In this tutorial, we are going to look at the solar system model of the atom. It's a continuation of our discussion of what constitutes the parts of an atom. We left off in the previous lesson with the nuclear model, where Rutherford discovered that 99% of the mass is concentrated in less than 1% of the volume. In that nucleus is all the positive charge. He also had a hint that there was lurking some other mass, but he wasn't sure its nature. But he could not figure out what to do with the electrons. He knew they were there. He knew there were equal number of charges, but he wasn't able to say with any definitive confidence that those electrons were orbiting the atom. The reason he said that is if they were orbiting, they should be giving off radiation and eventually fall into the nucleus. So there were other issues that had to be solved, and when Bohr came along, he gave a fairly simple solution. It worked beautifully for the hydrogen atom, but it kind of falls apart for heavier atoms. But at least it got the ball rolling, and for future physicists to take care of the other issues, it was still a pretty decent way to start. Okay, and the key statement that Bohr made was, he just said, well, electrons do orbit the nucleus. Okay, even though they orbit the nucleus, they don't fall into the nucleus. They don't decay by giving off radiation. And if he was asked why not, he had no idea. But he reasoned, if they did, then atoms wouldn't exist, nor would we. Okay, so the electrons have to be there. The only logical way to say that they are there and not fall in the nucleus is they orbit and they somehow have a stable orbit. Okay, so he did make one major statement about those orbits that are very, very different than planets around a solar system. Okay, and this is actually the key. Again, he didn't know why, but it worked. All right, he says, unlike the solar system, electrons are only found in specific energy levels. All right, that should be a familiar concept from chemistry. Now we're going to look at that in more detail. So if we go to this diagram off to the right here, he's saying if this is the nucleus right there, and let's say this is a hydrogen nucleus, you can find an electron here. You can find it here. You might find it down here at n equals 1, but it is never ever found anywhere between. Okay? It is like these lines here, these orbits are shelves in a deep hole. Either if you're a ball in that deep hole, you could be on one shelf, another shelf, or a third shelf, or maybe others, but you can never ever be anywhere between. And that's very different than our solar system, where planets can be anywhere as long as you're going the right speed. Okay? And the consequence of being in specific energy levels suggests that the energy of those electrons, okay, is quantized. And I write below that, not again. So here is yet another phenomenon in nature where things only come in specific amounts. Earlier we saw it was charge, and then a day ago we saw that the energy of a photon only comes in certain values, and now Bohr is suggesting another quantum idea. And you got to understand at this time, the idea of things coming in quanta was not very well accepted. It was too weird. It completely went against the classical idea of, if you will, a wave, an analog, where something could take on any value you wanted given certain conditions. Okay, but again, why does he suggest this if he really has no basis for it? And theoretically, because it worked and it explained a few things that nothing else could. And that's powerful. All right, so what's the consequence of having quantized energy levels? He was able to determine that elements have unique spectra, and I'll show you that in class because it's really important. Okay, in other words, atoms give off certain colors that no other atom can, because when the electrons are in a particular orbit, they can only jump from one specific level to another. Okay, if we go back to our diagram here, if I have an electron in the n equals 3 level, when it jumps to the n equals 2 level, there's a specific energy change. And that specific energy change can be related to the frequency of the atom. Okay, it says h nu, but we'll call it hf. And so what Bohr was doing is he was using Planck's idea that, put out about 10 years earlier to explain why you only get specific colors, because they correspond to specific jumps, and there's only so many jumps you can have because of the unique energy levels you are allowed. Okay, so each jump corresponds to a specific energy that in turn corresponds to a specific frequency. And again, that's Planck's law. and therefore a specific color. And this again is all according to Planck's law. Okay, so what we want to do in this lesson is really just apply the mathematics of this in a very simple way. So let's talk about energy levels, because that's really the key topic. So there's two things you need to know. You need to understand that all atoms have a ground state. All right, now, hopefully you remember that from chemistry, but let me remind you what it is. It is the lowest possible energy state. And that's where electrons want to be. By default, electrons will generally be found in the lowest possible energy state. Okay, they don't want to be in the excited state, which is the next one. Okay, to be in an excited state, you have to put energy in, and it'd prefer to be in the lowest energy. So what is an excited state? Well, it's above the ground level, and it's due to an input of energy. So if you have a hydrogen atom and you leave it alone, the electrons will almost always be in the lowest possible state. If you add energy to it, and there's a lot of different ways you can do that, you will excite them to higher energy levels, and they don't want to be there. Okay, so what happens when they're in a higher excited state? Fairly simple. They will spontaneously, you don't need to do anything. It's purely a random process. Okay, drop back down to the lower energy levels and eventually to the ground state. Okay, and in the process, they rid themselves of the extra energy in the form of a photon. In other words, they give off light. And the light that they give off is a specific energy, and therefore a specific frequency, and therefore a specific color. It's actually fairly simple and elegant in its own way, even though it gets fairly complicated for higher atomic numbers. So the equation we want to understand for this energy is a change in energy from a excited state to a different state is simply the energy of one state minus the energy of the other state. Okay? And when we do this, we always drop from a higher to a lower state. Okay? So you give up, let's see, we absorb energy. When you absorb energy, you go from lower to higher. Sorry about that, that's this smartboard. Okay, and then when you emit energy, it's simply high to lower. Okay, and that's important. So now let's look at some energy level diagrams. You have two of them in your reference tables. I will refer you to them in class. Right now, let's look at a sample one that you'd find in your reference tables. All right, this one is for the simplest, and that's hydrogen. So understand, these lines right here, here, are the orbits of one electron, the possible energy levels. The nucleus is down below here, and we're just looking at a tiny little portion of it because that's all we really care about. And so key information that we have on these energy level diagrams. First, you have on the right the quantum state or the level. N equals 1 is the same as a ground state. This is the lowest possible state it can be. Then it can jump up to 2, 3, 4, 5, 6. There's a lot more. And then when we have N equals infinity, then it has left the atom, all right? It's ionized. That's important to understand. It escapes the atom altogether is when you're at the infinite energy level. And then off to the left are the energies associated with those energy levels. Okay, don't worry about the negative. The negative is just basically telling you how deep in the hole you are. It's the number that we care about, the 13.6. And note the units are in electron volts. We'll take care of that in a little bit. All right, so let's look at a sample problem, and I want you to try one on your own before you come into class. All right, first question. How much energy is needed to excite a ground state electron to the third energy level, as shown by arrow A? So if you're asked to draw a transition, okay, A has been drawn for you. We've gone from the ground state all the way up to N equals 3. So an electron is sitting there, and we know that it's not going to stay there indefinitely. It's going to spontaneously drop down. So we want to know how much energy is needed. Okay, well, it's as simple as reading the diagram. The change in energy is simply equal to the initial minus the final. Okay. And therefore, I'm going to ignore the negatives. It really doesn't matter in here. 13.6 eV minus 1.5 eV. Okay, so the mistake that you might make is you might read this as it's gone, the energy there is 1.5 eV. That's true, but the change was the difference between where it started and where it finished. So that's going to give us 12.1 electron volts. Okay? Fairly simple. Now, why do we care that it jumped up to that state? Well, like we said, it's eventually going to fall back down. So we want to know how many different photons, all right, could be emitted on its way back down to the ground state, and draw arrows to show the possible transitions. Okay, well, I would think the obvious thing to say is it would drop from here all the way back down, just like it was a bohr. And that would be true. But that's not the only way it can get back down from 3 to 1. It doesn't have to do it all at once. Okay, so it could also drop from 3 to 2, and in the process, in that simple little transition, it will give off a photon. This will give off a photon of a different energy. Okay, and if it goes from 3 to 2, well, it's not going to stay in 2, so eventually it's going to drop from 2 to 1. And that's going to give off its own photon. So we get 3 photons given off for 3 different possible jumps on the way back from 3 to 1. Okay, so there are 3 of them. And we can calculate the energy very easily by looking at the differences. All right, so next question. What would be the energy, frequency, and color? So 3 things for the lowest energy transition from 3 to the ground state. Okay, well, we've drawn all the possibilities. So what would be the lowest energy? Well, that should be pretty evident. It's the one with the smallest jump. Okay, so it would be this guy right there. So what we're really talking about is, so our solution is, let's first of all find the smallest jump and calculate the energy. Well, the jump that we're talking about is from 3 to 2. All right, not 2 to 3, but from high to low. And that energy is going to be 3.4 minus 1.5, okay, and that's going to give us 1.9 electron volts of energy. All right, so we've answered this part. Now we want to find a frequency that corresponds to that. All right, before we do that, we have to convert electron volts to joules. And don't forget that our conversion factor is there. So if I take my thing I'm trying to convert, 1.9 EV all over 1, and here is my conversion factor. So I want 1 EV on the bottom, 1.6 times 10 to the negative 19th joules on the top. Now I multiply those. That should be pretty straightforward. And I believe I get 3.04 times 10 to the negative 19th joules. Okay, so it's a very small amount of energy. Now we want to translate that to a frequency. Well, how do we relate energy of a photon now? Okay, so this is the energy, not only of the transition, but this is also the energy of the photon released. And that's the key understanding that you want to make. When the electron jumps back down, it gives off energy in the form of a photon. So we can use Planck's equation. We can say energy of a photon equals HF. We know that the energy of the photon in joules is this, equals Planck's constant times F. Okay, and oops, get rid of that J. And if I solve for F, right, that should be pretty straightforward. I get about 4.6 times 10 to the it should be positive 14th hertz. Sorry, this is so sloppy. I'm in a rush a little bit, so let me erase that. I think I have a minute. Okay, now how do we find what color that is? Well, we go to our reference tables. We go to the spectrum part, and we find out which color corresponds to that particular frequency. And so I see that red is 3.84 to 4.82 times 10 to the 14th. So this falls right back there. And so that gives us red. So that transition is a very specific red, and that's one of the signatures of hydrogen. Okay, so D, what minimum frequency photon is needed to ionize a ground state electron as shown by arrow 1? Okay, you do the same steps above. So if I want to go from ground state right here and leave the atom altogether, I want you to try that on your own. Figure out how much energy that transition corresponds to, and then convert that to a frequency of a photon. Okay, good luck.